Now, I know that if I had given you this picture, you could probably reason through the same thing and set up dx, dz, dy ordering, but ignore that. Maybe do it as a fun exercise for yourself to practice setting up bounds of integration. But we're going to assume that you were just given this and you had to come up with this. And so what I'm going to do is I'm going to write all my bounds as relationships real quick. So I know 0 is less than z is less than 1/3 6 minus 2x minus y. I know that 0 is less than y is less than 6 minus 2x. And x is between 0 and 3. That's the information that was given to me over here. Now I want to write my first bounds for x. And so these bounds, the lower ones, 0, 0, 0, those didn't depend on x, y, or z. So I can go ahead and keep them. I know that x is still bound below by 0 no matter what, because x, y, and z are all positive. And my upper bound should be in terms of z and y. For y, z is second. For z, it can only be in terms of y. And for y, it has to be a constant. If I do anything else, then I wouldn't be able to evaluate this integral. If the middle one depends on x and y both, then there's a leftover x at the end of my integral and something went wrong. So if I know my upper bound for x is the one that can use both z and y, then I'm going to look for something that uses y and x. There we go. And z. So I knew that z is less than or equal to 1/3 6 minus 2x minus y. So that means 6 is less than or equal, getting ahead of myself. 3z is less than or equal to 6 minus 2x minus y. And let's see, I'm looking for something about x. So let's isolate x. So I just moved my x over to this side and my z over to the other. So x is less than or equal to 1/2 times 6 minus y minus 3z. So what I did was I used the bound that included the most variables, and I just solved for the new variable that I want the bound to actually be for. And so now I have an upper bound for x, 1/2 times 6 minus y minus 3z. And I'll do a little star there, little star here. Now I'm looking for the bound for z. And this is where it gets tricky because I have a z, but I already used this function. And this function that I haven't used yet depends on y. So if you go in here and you try to do like y less than or equal to 6 minus 2x, that's just going to lead you to something that's y in terms of x, but x is already gone. So from here you have to remember that our bounds of integration are determined by the shadow of the prior bounds. So again, we're just going to say, okay, when this plane runs into this x equals 0, I should get a line that tells me how z and y are related. So we say, what happens when 0 is equal to 1/2 times 6 minus y minus 3z? I'm going to get 0 equals 6 minus y minus 3z. I'm going to get y equal to 6. Oops, I'm sorry. I'm solving for z. I wanted to like switch every variable, but it keeps tripping me up. So I get 3z equals 6 minus y, z equal to 1/3 times 6 minus y. So 1/3 6 minus y goes right there. And then my last bound, I do the same thing. I say, okay, I don't even have to plot it. I know that I'm casting the shadow of this line and 0 hitting each other. So I get y equals 6. So my upper bound for y is 6.